I'm going to talk today about kind of adding onto the graph with something like Kafka. So how do you integrate Neo4j graph technologies in with the other systems that you're dealing with? We could also think of this talk as kind of a combination of streams, tables, and graphs, and of course a little bit of a lighthearted spin on that. So we're going to look at how all three of these technologies or all three of these capabilities can come together and work together well. My name is Reif. I'm a Neo4j Labs engineer. So I work on a lot of the projects, the integration projects that allow Neo4j to connect with other sorts of technologies. We do have a limited time today, but please do feel free to reach out to me, email, Twitter, LinkedIn, however you're most comfortable. I'm happy to continue the discussion or answer questions at any time. So if you're familiar with the Kafka world at all, you might have heard of this stream-table duality. Where a stream is kind of like a change log of a table. So it records the history of all of the changes made over the course of time. And then your table is a snapshot of whatever the current status is of the data or a particular status at a particular time. Most applications, you can use a combination of these things, one or the other or both, just depending on the use case. However, we want to kind of add a third dimension into this, which is adding in a graph layer. So you're dealing with recorded history, a sequence of data records. Tables, you're dealing with mostly key value pairs, current status of data at a particular time. And then graphs add another dimension to this. So it allows you to integrate all of these data sets together and look at how they're connected, what are the relationships among the data, and combine that with things like graph analytics over the course of the entire graph, over the course of all of your data, to kind of get some real insights based on all of that group data together. So hopefully you guys know a little bit about what Neo4j is, but if not, graph basically mimics the real world. So data and society around us is all very, very interconnected. One good example of this is social networks. Facebook, for instance. So looking at how people are connected to one another. Not necessarily the individual pieces about the person, but really about the relationships between different people. Even things like our companies, markets, global industries, all of this is increasingly becoming more and more connected. The world is becoming smaller. Even things like logistics and routing. How do I get my products and services or route people or whatever you happen to be dealing with? How do I logistically make sense of that? What is the best way to get resources from one point to another? There are a variety of use cases for Neo4j. So the social network example is a common one, but we deal with a lot of other situations outside of that. So anything from internal applications to external customer-facing applications, master data management, where did this piece of data originate and what's the source and the definition and all that good stuff about it. From physically routing your IT network, switches and cables and all that good stuff. And we're going to talk more about the fraud detection example in this session today. So I won't dive into that too deeply just yet. But real-time recommendations based on a user's history or what they're connected to in the graph. What can I recommend to them for products or services? Graph-based search. How can I give the most relevant, detailed information for something a user searches based on what they're connected to and the history behind that? And then identity and access management. I have users that have access to resources. Why is it that they have that access? What are they connected to that grants them certain roles and privileges? So we're going to take the perspective of just a typical software developer. We're naming him Paul. So works at a large financial firm. We're going to call Piggy Bank. So just doing his typical day job there. And one day the boss comes into the office and says, hey, we're having a lot of issues with fraud detection. We have accounts that are being hijacked. We have fraudulent transactions being made. A lot of money's being lost here. We want you to design a fraud detection system to try to prevent this. Now, I will say up front, this use case is a real Neo4j customer use case. However, we've obviously changed the names and blacked out a lot of the data, so it is all fake to protect those involved. But this is a real life scenario here. So he needs to build a fraud detection solution. So naturally, being the confident developer that he is, he's like, sure, absolutely, I can totally give that to you. Give me about 3 weeks. So now he has to figure out where he's going to start, what he's going to do. So like any good software engineer, he goes to Google and searches fraud detection. And starts looking through the list of results there. OK, Neo4j comes up on the first page. Let's look a little bit more about what this is. We need to figure out how it's being used to fight fraud detection or to battle fraud, and figure out how we can sort of use this and what it does. So he comes across a GraphGist here at the bottom, which is basically a live use case that our community members or customers have posted on the website so people can interact with that particular scenario, run some sample queries, look at the data, and interact with that information. So he's getting all of that and is starting to think, OK, this might be something. We're looking at the connections in the data, how all of this is related, how it fits. So this might be something that I can use to battle fraud. Obviously, other people are doing it, right? So week 1, he's going to start with, I need to figure out this Neo4j thing. It's totally new to me. What all do I need to learn in order to use this? So Neo4j is a transactional graph database. So first of all, it's a DBMS, and it uses the property graph data model. So probably something he may not be familiar with, so might want to kind of dig in and get a little bit more about that. The Cypher query language is what we use to query graph data. So you can kind of think of it like SQL, but it's designed for graph theory, so based on the patterns and traversals of graph theory. And then just some of the capabilities that go along with that. You can add graph analytics. You can do data visualization. We have some developer tools for building applications. So far, it seems like it's checking all the boxes for what Paul needs for his system. So, and just quick note, the Cypher query up at the top there, that is what kind of Cypher looks like. And we'll explain a little bit more about that as we go along. But he's got some good ideas, has a decent foundation for what now he needs to tackle in order to use this. So the property graph data model is basically entities and how those entities are related to one another. So you can kind of categorize your entities. As you see here, we have an employee, we have a company node, we have a city node. Each one of these nodes is being categorized into kind of a different tag or a different category. And then we add those relationships between. So a company has a CEO that happens to be an employee, typically, and that CEO has started at that has been a CEO since a particular date. So we're adding now some name value pairs that are properties to give the data a little bit more information and background. We have a particular employee with a name, date of birth, employee ID, and that company is located in a particular city. So it allows you to focus really on the individual entities and the relationships between those, and then add a little bit more detail and context to your nodes and relationships in the form of properties. So Cypher is the way that we put data in and take data out of Neo4j, typically. And so how do we construct a Cypher query? So if we wanted to create this information in the database, this Neo4j is located in San Mateo, we would start with this statement here. We have a create keyword that's basically like an insert. And then we need to create 2 nodes. We need to create our Neo4j node. We need to create our San Mateo node. And so our Neo4j node is a type company with a particular name, property. And then we have our other node on the other side. That's going to be a city type node with a name of San Mateo as the property. And then we need to draw that relationship in between. So we're adding what type of relationship exists between these 2 entities. Neo4j is located in this city, San Mateo. And so you can kind of see how very, very similar that Cypher statement looks to the visualization that we show above it. So your nodes are encompassed in parentheses. You bring that together, it forms a circle, which is the node. You can kind of see the arrow for the relationship going between the nodes with that relationship type in a box. And so again, very visual. It's based on ASCII art, so it's very powerful, but it's also based on the patterns and visual patterns that we're used to seeing. So you can also write Cypher queries using our Neo4j browser tool. So Paul has kind of figured out Neo4j browser and how to interact with that. So it allows you to write statements, queries, and such, and interact with the database and the data in it via a web page. And so this particular Cypher statement is just looking at user recommendations. So it's doing a match, which is kind of like a select. So find some recommendations for me in the database. You can also view the data as a visualization, which you can see there with the pretty picture that shows up there in the middle. Or you could return it in some other types of format as well. So this is pretty good for getting around and navigating the data in the database itself. So here's kind of what the architecture that he's dealing with outside of Neo4j. Because if you're most probably companies, you're not dealing with a single database in a silo. You're probably dealing with a lot of different databases with various amounts of data in various places, and you need to somehow pull all that data together. So you might be dealing with customer data that's sitting in a relational database like Oracle. You might be dealing with account data that's sitting in a columnar store like Cassandra. And then you might have session data and cookies and web session information that's stored in something like Redis. And how do we bring all of that data together into something that's meaningful? So what he needs to do is bring all of these disparate sources of data and pump that into Neo4j and pull all that data together and see how it's related and connected in a graph. So combine all those and then try to pull out the suspicious parties, the suspicious information, things that are connected that shouldn't be connected. And then from that, identify the potential fraud rings and flag those so that someone can look at those and go, yes, this is fraud. We need to do some sort of action on this to prevent that. So how are we going to determine that we have something that's fraudulent? What Paul comes up with is that we're looking for some overlapping identity pieces. So in this case, we have 3 persons here, and they might share things like a social security number, a phone number, a web session cookie. All of those things together don't look too normal, let's say. So sharing a cookie, if you have users where their session has been hijacked, then that fraudulent person has hijacked their session and therefore is doing fraudulent activity. If you're sharing social security numbers, probably not a good indication that those 2 users shouldn't have that same piece of identity. And then of course, phone number, maybe not in and of itself an identifier, but along with some other information could definitely be an indicator of suspicious activity. And then try to find out who are these entities connected to. So who are they related to? Are there other sources and overlapping identities that people have besides just a particular single case, where together it looks like a complete picture of fraud. So this is the data model that Paul comes up with. We have parties, or customers, however you want to think of it, but we have these financial parties. They have accounts, they have credit cards that are all associated with them, they have web session cookies, and then we've separated out social security number, phone, and address as being separate nodes. And that's so we can see where those nodes connect to other entities and kind of follow that pattern traversal very easily. So we've segmented all this information out. We kind of get a good picture for what our current data looks like in all these different systems and how to bring it all together into the graph. So he can bring all of this information in. He starts with a load CSV, which is a command that's available in Cypher. So he takes the customer data, the account data, and the session data, and basically exports those all as CSV files, and then is able to use load CSV to get that into the graph. So he reads that row, that very tabular data structure, and says, how do I want to transform this into the property graph model that we looked at? And so in his case, he's creating parties. That's that merge party. He's setting a few properties for each of the parties. And then he's creating the social security number node and tying that back to the original party. Then creating the phone number node, and again, creating that relationship back to the original party. So that's all he's doing. He's taking that row tabular data format and transforming it into a graph pattern that you see there at the bottom. So now that he's got the information all dumped in there, he needs to kind of query that and start looking at the graph data. So this is where he can construct some Cypher. He's going to look for a particular pattern, which we've defined as a variable path, where you have a party that has a social security number, phone, or cookie relationship to any other node there in the middle that also has another social security number, phone number, or cookie relationship to another party. So basically where you have two parties sharing a piece of identity, or they shouldn't. Then return all of those patterns. And of course, if you have thousands, millions, billions of nodes and relationships in your graph, you could get tons of instances of this. So right now, we're only going to say we just want to pull 10 of these instances, just to kind of get a look at them. So what he's going to come back with is something like this. The red nodes are your party nodes, so those are your users. The green nodes are phone numbers, and the blue nodes are social security numbers. So you can already see several instances where you have red nodes, your parties, connected to social security numbers and sharing social security numbers, the blue ones, which probably isn't a good sign. But we need to actually go one level out from this. So we see some users sharing some of this information, but that may not be enough to tell us, do we have a fraud ring that's going on here? If we go out one more level, is all of this stuff connected somehow? So to find the fraud ring, we're just going to extend that and do this variable length path, which you can kind of see out towards the end of that top line with the star up to 2. It's a little hard to reach over there. Where we can go out an extra 2 hops. So we're looking at where users share an identifying piece of information, and then we want to go out 2 more hops from that path and say what's on down the line from just that limited pattern. And then we're going to return all of those patterns, and we're going to say, OK, now we only want to return up to 100. So we're looking at just a little bit bigger size data set at this point. And so we get back something like this. So the dark blue nodes then now are cookies. So we have our parties in red. The light blue are the social security numbers. The green ones are phone numbers. And so you can see there's a lot of users sharing all of this information. And it might be something where we've now uncovered a lot of fraudulent activity where you have this ring of users that's hijacking sessions or sharing social security numbers that then uncovers a larger activity that we need to investigate further. So Paul doesn't want to just run this query every so often and pull the data. He actually wants to automate this and allow a process to pick this up automatically and flag it for further follow-up. So you're going to be linking possible innocent people who have had their sessions hijacked or the social security number stolen, to potential suspects that then have taken advantage of that information. And so we're going to take this query there up at the top, which is going to look at those overlapping pieces of information, and then say that these parties are associated with one another. So it's creating that associated relationship between the two parties. Then in the query on the bottom, we're going to iterate over that data and run something called the Louvain algorithm, which is clustering all of this data into communities and saying, OK, all of these users are interrelated and they tend to cluster together very, very well. So this is a community we might want to look at. And it's looking at where parties are associated with other parties. So you'll end up with these kind of clusters and groupings of nodes where you have users that are interacting with other users very closely. And so it's going to run every so often to pick those up and flag those. You can kind of see the set property kind of second, third line from the bottom there, where it's going to set a property to say, we want to follow up with this. This is the community that these users are in, and then we want to follow up with this community and take a deeper look whether this is actually fraudulent or it isn't. If you're not familiar with the Neo4j graph algorithms library, we have a wide variety of kind of categories of algorithms that you can run. So pathfinding and search just looks at routes and pathways through a network. Centrality importance is looking at the importance of individual nodes or the influence of those nodes over a network. Community detection, which Louvain is part of that grouping, looks at how nodes tend to cluster together or break apart into different communities. Link prediction looks at the possibility or the probability that new relationships will form in your graph. And then similarity just does a calculation to see how similar nodes are. And if you guys are interested more in the graph algorithm space, we do have graph algorithms books. So I don't know if you guys have seen those out in the hall. They're handing some of those out today. You can also get a free ebook copy if you go to this web page here, and that's still able to be downloaded as well from that. And that includes discussion on all of these algorithms, as well as a chapter on machine learning with examples in both Spark and Neo4j as well. So these are all the algorithms that we have within those high-level categories. This is constantly growing. I believe we've added 1 or 2 in the last month or so. So feel free to go out and check out the documentation just to make sure everything's up to date and you have all the latest and greatest stuff. Most of these are variations on a theme, but depending on what type of data you're looking at, you might need some of those variations to get the results that you're looking for and pinpoint the proper structure for what you're dealing with. So feel free to go out and check that out if you want more information. So just in case you might be thinking Neo4j has made this up and kind of ventured out on their own, we are not the first to start using algorithms in this space for fraud detection. So there's a book called Fraud Analytics. There's only one chapter that discusses Louvain on graphs. However, if you're interested in just fraud analytics in general, this book is a good one to start with. So the Louvain algorithm, which is what Paul has decided to use, he calls it like this. So it looks similar to a cipher procedure call. He's calling the algorithm.louvain and then passing in a cipher query, looking at the parties that have those overlapping identities, and then pulling that information, the calculations back out for what nodes fall into what communities. And just to back this up a little bit more, there are over 48,000 US patents for graph fraud and anomaly detection over the last 10 years. So even without graph databases and graph technologies in general, this stuff is still being used in the fraud detection space. So this is nothing new in this area. So okay, Paul feels pretty good about this. He started to look at algorithms. He's got the data in Neo4j, all these connected disparate sources of information all dumped into the graph database. But it's still not good enough. So the boss comes back and says, okay, that's great, but we're not going to be dealing with static data. Things are constantly going to be changing, constantly going to be updating. We're going to get new updates and inserts and such to our other data sources. We need this to be streamable. So we need it to update and learn as we go. So that's where something like Kafka is going to come into play. So Kafka allows you to do streams and messaging, basically, for when you get changes. So this is what Paul had been doing at Piggy Bank. He had taken the customer accounts and session data, pulled those into the graph using that load CSV that we looked at. But this is kind of the higher level architecture that he's dealing with right now. So we already have Kafka tying into our customer account and session data storage layers. We already have those events going back and forth to notify those different data stores, hey, there's a change, or hey, we need to feed this information elsewhere. So that's kind of an extra layer that we don't really need. What we want to do is plug Neo4j directly into that transportation layer and say, as messages come through from other systems, we want it to feed to the graph as well. And so that's where the Neo4j streams library is going to come in. So this has been a somewhat recent development by the Neo4j labs and partner solutions teams. And it provides a couple of different capabilities. If you want some more information on that, the link down at the bottom, neo4j.com/lab/Kafka, has more information about this library. But basically, it allows you to take in messages from a topic coming from other systems and write those to the graph. And then it allows you to do the reverse. So I want to take something has changed in my graph, and I want to push that to other downstream processes. So I can take that information from the graph and push it out to a Kafka topic in a Debezium type format. We do have a verified gold connector out on Confluent Hub. So that's a good way to use this integration here to get data in and out of Neo4j. This is a good way to start, and allows you to be very flexible to determine what you want to pull from Kafka and determine what needs to go into Neo4j and what needs to come out and such. So this is the infrastructure we want to try to get to. We have all of our existing systems that are already feeding that information into Kafka. We want to take all those changes that are coming from those other systems and basically create a party interaction system that gets pushed over into Neo4j. So whenever we have parties that change or links and relationships that change, we want that information to go into the graph. So this is how we're going to configure it. The top one there is taking messages from a cookies topic and creating a new cookie in our graph that connects to the right party. So you can kind of see the Neo4j streams sync topic cipher cookies there towards the top. That's the topic it's going to come off of. And then we're taking that message that's coming in from Kafka, and we're creating a graph pattern from that. So we're creating a cookie node. We're setting some properties on that. We're linking up the related party for that cookie node, and then creating the relationship between those parties and cookies. And then down on the bottom half of the screen is the process going back the other way. So when something changes in the graph, we want to push that back out to Kafka. And you can see we have two different topics that are going out, one for fraud flags. So looking at any type of change that's going on in the party nodes, anytime you see a change for party nodes, you want to push that back out to the fraud flags topic in Kafka. And then the next line down is anytime you have a change in the associated relationships in the graph, you want to push that out to the relationships associations topic in Kafka. So anytime you have changes in information for new cookies coming in, we're going to change that in the graph. Anytime you have those party or associated links changing inside the graph, we want to push that back out. The way we can get from a graph structure back to the table format that Kafka and other systems might deal with better is we can use KSQL. So Neo4j Streams allows you to publish the change data capture back to Kafka. And the query that's down in the lower right-hand corner there is basically doing that. It's taking two different things. So where you have information in the graph that is set for follow-up. So this might be fraud, you need to follow up with this. Or we've confirmed it's fraudulent that in the graph. Then we want to pull that back out with KSQL, with this particular KSQL statement, and push that to other systems. So you don't need to use anything like Cypher. You can if you want. But this allows you to kind of translate that data back into the tabular format that Kafka and other systems might work with. You can run all of the stuff for graph analytics and KSQL and all that good stuff in the Confluent Cloud. So if you're interested in interacting with that more so, you can do that in this format as well. OK, so he has Neo4j set up, and that's going really well. He's figured out how to plug that into Kafka and get the information passing back and forth to and from other systems into Neo4j. But now we've flagged potentially fraudulent activity. But we still need a domain knowledge expert to review those and say, yes, this is actually fraudulent, or no, we have something that got flagged unnecessarily. And so he needs a way to expose this information where the analyst team doesn't have to go in and run queries and look at code and all that good stuff. So basically, we need a filtering system. We need to take the account activity and the things that Neo4j has flagged as being potentially fraudulent. We need to funnel that and filter all that information down so that the business analysts can look at it and then investigate that further and determine whether or not they need to do anything about this particular activity or grouping. And that's where we can plug in things like our Neo4j client drivers. So you can build applications on top of Neo4j using a variety of programming languages. So anything that pretty much suits your fancy, we probably have something in there. And it provides all the capabilities for dealing with clusters, running with our Bolt binary protocol, and other sorts of things that are pretty standard data transfer to and from a database. So taking an example from the JavaScript driver, it allows you to run Cypher queries and pull that data back from Neo4j using our driver. So you can kind of see we're setting up the Neo4j driver there at the top. We've got a query. We're going to create a session. We're going to run that query inside the session and then return those result sets back that are coming back from the query. Now, there are a few other things we can integrate with. One of those is GraphQL. Is anybody familiar with GraphQL? A few, not terribly many. So GraphQL is basically an API query language. So you can kind of think of it as an alternative to REST, but it allows you to kind of customize what you're returning and how much data you're sending over the pipe. So it works really, really well. We do have a full stack offering that goes along with GraphQL really well. It's called the Grand Stack. So it uses GraphQL, React, Apollo, and the Neo4j database. That's the Grand. And then, of course, it's full stack. And you can find out more information on that at grandstack.io. There's even a starter project out there, which is what Paul's going to end up doing. He's going to go out to that website and, ooh, this looks nice. It's all kind of set up and templated out for me. All I'd have to do is build the components. The nice thing about GraphQL is it exposes application data as a graph. So obviously, if you're dealing with a graph database on the back end, you kind of get that full experience of graph all the way through. You're not having to do the resolvers and the translations between different data formats. It's all kind of formatted the same way. So that works really, really well. And you can expose that GraphQL API from Neo4j and pull that information exactly how you want it. Again, those resolvers are included and kind of built out of the box for you. So that's pretty simple and easy to get started there. And so Paul has kind of built this grand stack application that allows users to go in to a React user interface. It pulls data from Neo4j using GraphQL, and then kind of has a few different pieces involved in the interface here. So over there on the left-hand side, they can look at either cases where we have this kind of fraudulent activity, or they can look at individual parties that could be fraudulent. You can select a particular case in order to determine this is fraud, this is not. You can make your decision based on that. And then you can see down in the lower right-hand side where we have that pretty visualization. That pulls all of that data in, so then the analyst can look at it and actually explore the graph and kind of dig into different nodes and see all the relationships and look at this more visually to determine, yes, this is fraudulent, no, this is not. So our full technical solution then is that we're bringing data in via Kafka from various other systems using the Neo4j streams library. That information is getting put into Neo4j. We've got a background process running every so often that is iterating over the graph and running the Louvain algorithm so that it flags potentially suspicious communities and groups of parties. And then we have this grand stack application that sits on top that allows your business analyst to dive into the information a little bit more, sift out and look through and explore those communities and determine whether it is actually fraudulent or not. So let's actually stop talking about this and let's switch over and do the demonstration. So we want to look at something a little bit more real here. First, I'm going to show a little bit of the code, which hopefully that's somewhat readable. So remember, I talked early on in the session that we have information coming in that we need to create new cookies in our graph. And so that's what this little piece of code here is doing. So that's that cipher statement that's creating new cookies from information coming in off Kafka topics from other systems. And then we have the reverse that's also put in here. So whenever we have changes to parties or associated links, that information is getting sent from Neo4j back out to the outside world through Kafka. It is running, so this is the setting that association link between your party nodes. So this is, it's running periodically every minute to say, okay, anything new in the graph, I want to run this cipher statement and create those association links between our parties. And then we have that Louvain algorithm that's running every 2 minutes that iterates over those, all of that information and looks at the different communities and then creates those communities and whether you need to follow up with this particular community or not. So that code that I talked about early on in the presentation, this is actually where it's being called and run. So let's go over and look at our front-end application now. So this is the grand stack application where users can interact. Their fraud analyst team can interact and determine whether something is actually fraudulent or not. So you can see we have either, we can look at the case view or we can look at the different parties, which is what I have on now. And we've categorized this where we can sort by how many identities are being shared with these users. So you can kind of see, I don't know if I can, that's a little better. Chad right there at the very top is sharing 25 different pieces of identifying information. That's probably not a good sign. So let's kind of take a little bit of a closer look at this and log in. So this is a tool called Bloom, a Neo4j Bloom. It's an exploratory analyst tool that allows you to kind of look at different pieces of the graph in a visual format. And so we're looking at this individual case, and we can kind of zoom in a little bit. And see we have individual parties, so those are the ones in pink. This is Chad Wright that we initially clicked on. You can get a little bit more information about him. We have other users that he's connected to. We have social security numbers in red that are all kind of tied in this different community, as well as cookies in green and so on. So this allows the business analyst to kind of interact with this data, kind of pull it apart, look at the relationships and the connections there, and then decide this is actually fraud or this isn't. So he can go back to the interface, whoever is analyzing this or looking at this information, and they can choose whether this is fraud or not fraud. And basically what this does is this flips a Boolean in Neo4j, sends that information back to Neo4j, updates the data in Neo4j, which then causes a change to go through and head on out to other systems, downstream impacts. So either send this to the legal team, say we need to do something about this, or just close the account in general. So this allows the analyst to make this decision after they've analyzed the data in this type of format. So just quickly to look at the GraphQL playground, the API. So this is just looking at the data that's coming from Neo4j. GraphQL, the API, is pulling this for us, so we can run here. We're just looking at parties. Where the case ID isn't empty, and you have a fraud follow-up set to true, and the fraud confirmed set to true. And so we can pull all of these properties, basically, the variables, and run that. And this will run against the database directly, Neo4j, and pull that information back. So we have this guy, Pierce, and he's using 22 other shared identities. And you can see a little bit more information. So this is just that link that's directly on top of the database. This is the API that GraphQL is allowing us to kind of create on top of Neo4j. So let's go back, and we'll kind of wrap up here with some resources. So I did mention, but if you saw PII that was in the demo data set, this has been all wiped clean. They're sample data, so it's nothing that's actually real life. We've masked all of those real numbers to protect all of that PII. So the schema and the use case is real, the data is not. So wrapping up here, Paul has done a really great job. He gets that elusive 10x engineer trophy that all developers are striving to achieve. The boss is really happy because he's done a great job and they've got a solution in place. And Piggy Bank is happy because they've saved them a ton of money and are actually pulling out these fraudulent users now and keeping track of all this information. So just to kind of wrap up a little bit, if you're interested in more information on the Neo4j Streams library, you can check out the code there, as well as the Connect Neo4j sync on the Confluent Hub. More information on GrandStack is at that grandstack.io link. And then there's an example out there of using Neo4j Streams to build a data warehouse. So that's a good blog post that's sitting out there for that. And then, of course, just general information about graph algorithms, how to use them, what they're used for, and how you can apply those can be found in our documentation. And then if you're interested, Max DeMarzi has a session actually after this one. I think it's in the other track. And he's written a couple of blog posts on fraud detection, has some good information out there as well, so feel free to check out his session. Also, I don't have this up here, but Anurag is talking a little bit more about Bloom. So I had the visualization analysis tool that I had up there. Anurag is kind of over all of that, and so he's talking a little bit more about that here later today if you're interested in that as well. So here's the code finally if you guys are all interested. There's a good README out there for this that should hopefully walk you through each of the steps to allow you guys to replicate this and duplicate and get up and running with that code, hopefully pretty easily. Feel free to let us know if that's not the case. We'll try to continuously improve, but it should be able to be copied and downloaded. You can run all of the stuff that I just showed you today on your own as well. And of course, please do feel free to reach out to me. I'm happy to talk either after this session out in the hall or via email, Twitter, LinkedIn, however you feel most comfortable. So thank you guys very much and enjoy the rest of the conference.